Hi all. This is an overview recording discussing the Telcoin network system smart contracts, and the target audience are the security researchers and auditors, hackers who will be looking through the repository and sort of battle testing, hardening our code from a security standpoint. So let's get started with an overview. The Telcoin network smart contracts repository contains various system and standard contracts. They provide different functions and serve different roles for the chain. And to back up a bit, Telcoin network is a layer 1 blockchain, which is EVM compatible, and it will be powered by the Telcoin token, which was an ICO in 2017, ERC20 on mainnet Ethereum. And so for the scope of this audit, there are a handful of contracts within scope. They are largely critical for the chain. And so the overview here, there's different ways to build the repository. The main thing that needs to be kept in mind is that we are using NPM because of the requirements of certain dependencies, mostly the Axelar Interchain token service required that, and so rather than use the standard Foundry submodules in a lib directory, all of the dependencies are installed into the node modules directory, and those can be installed according to the README here. So the first contract to talk about is the consensus registry. And so the consensus registry is a system smart contract that's implemented in Solidity. It serves as a single on-chain source of truth for consensus items, things that are relevant to sort of network-wide consensus state. They use EVM storage as it is a Solidity smart contract. And so the consensus registry's roles can be broken down into four major components. On the one hand, it manages the consensus NFT whitelist, and that is because the validators for Telcoin network are MNO, mobile network operators, who must be whitelisted and approved, vetted off-chain via the TAO, which is the governance arm of the Telcoin organization. And so the consensus registry contract, specifically its stake manager implementation, handles an ERC 721 ledger, an NFT, which is called the consensus NFT, and it represents consent by the TAO to operate a validator, a node. So it also oversees the TAO staking mechanisms. So the consensus registry, like I said, inherits the stake manager contract, which handles stake locking for the validators who are approved by governance, i.e. issued a consensus NFT. And it tracks, distributes, and handles slashing for the tree itself. Also manages the active validator set. There is an entry queue, or an activation queue, I should say, as well as an active status and an exit queue, and an exit status at which validators may unstake and exit from the network. And that is to ensure that public keys such as ECDSA or BLS keys cannot be reused. And the last item, which is overseen by the consensus registry, is storing historical epic information. This is done on a rolling basis using 2 ring buffers, and essentially the epic information is stored as well as 2 epics in the past. So the epics are available in contract storage on a public ledger, the public EVM storage, so that members watching the network can sort of perform verification that the network-wide state is accurate and correct. So we went over these 4. One thing to keep in mind is that the system calls for the consensus registry are done from a specific address, which is determined by the maximum U256 size -1, so OXFFF. And that is, the logic for that is quite simple, but it's contained in the system callable parent contract abstract contract, which is inherited. And those system calls are done to specific functions within the consensus registry, namely the conclude epic, apply incentives, and apply slashes functions. Those must happen in a specific order, where conclude epic comes last, and it's done on the epic boundary invoked by the protocol itself, which is why it's called a system contract. Going into the validator onboarding portion of the consensus registry, there is a one-directional lifecycle for a validator. These are tracked by an enum. I'll show you those after this quick overview here, and point you as well in the direction of a number of helpful markdown files, which document invariance, design, architecture, that sort of thing. But we'll get there. So for validator lifecycles, there is the whitelisting portion, which I discussed earlier. Gain approval from Telcoin governance, receive the NFT, perform a staking action. This can be done either by the validator or a delegator. Oh, excuse me. And this secures participation in the network as a validator entity. Once the funds, the TAL is staked, the delegator specifically needs to perform a relatively in-depth handshake with the validator. So the assumption there is essentially that validators and delegators must have an off-chain relationship. They have to exchange things, an EIP 712 struct hash. They have to exchange BLS public keys, and they also have to sign over, the validator has to sign over using their ECDSA key over the delegation struct itself, basically to signify consent for delegation. So worth remembering that those two entities have an off-chain relationship if present. Activation is self-initiated, and that is called by the node operator, so the validator and another nomenclature. And this enters them into the activation queue. This pending activation enum is what labels that. It happens at the next epic is when that enum is transformed into active. So the activation queue is quite short. It is only for the remainder of the current epic. The exit queue is a different story, which we'll get to. So at the end of each epic, the protocol performs a system call. This would include some other functions as well, like apply incentives and apply slashes, but conclude epic is the main one that sort of updates from the contract's perspective the epic state. So this processes the pending activation queue, and they are transitioned to the active state. Exit requests are also a self-initiated action from the validator. Validators choose to enter the exit queue. They have expressed a desire to retire. Nice. Which places them in the exit queue, where they must remain active and eligible for voter committees until the protocol finalizes their exit. How that is done is documented in some of the design files that we'll get into, but the main thing to understand is that the protocol determines validator exit after the validator has issued a request, a desire to retire. So yes, I guess that we just fully executed. So the actual qualification, the actual requirements for exiting are for the validator address that is in the exit queue. If it is excluded from voter committees for 2 consecutive epochs, this is determined by the protocol, then it is deemed ready to be exited, and that happens as a part of the conclude epic flow. The unstake function is only accessible once a validator has reached exited status. This can be called either by the delegator or the validator, and this will reclaim original stake and any accrued rewards or slashes. One thing to note is that the economic incentives are always delivered to the delegator if one is present. So if a validator has a delegator, all of the funds, stake, rewards, all of it will go to the delegator. And the expectation is that because there is an off-chain relationship, that delegator, it can be a smart contract that supports EIP 1271, in which case that smart contract itself can codify sort of the dispersion or the splitting of accrued rewards and original stake between the validator. It's sort of an agreement, a contract between the two entities. But the delegator address, whatever is at that address, is what is going to receive the funds and then can be further codified in a Solidity implementation. So this reaching the exited state and retiring, it is permanent. It burns the consensus NFT, and the validator, it cannot rejoin using the same keys. It must provide new ECDSA and BLS keys in order to rejoin. Yes, and that's the design file, which we will Yeah, let's move there now, actually. So the design for the consensus registry here, a lot of this we've already gone over. We discussed a bit of the consensus NFT, which is essentially a whitelist curated by the TAO. The validator permissioning represents governance approval. The consensus NFT does. There are roughly 700 MNOs. There's actually some outdated information here. I apologize for that, but generally these ideas are correct in the design file here. The best place to look for the most up-to-date information will be in the interfaces for each contract, which I'll show towards the end. And then there's a section on system calls with the conclude epic, the apply incentives, and the apply slashes, which I've mentioned. There are certain nuances to this. The incentives involve an issuance contract, which accepts TEL for rewards from the TAO governance address. These are not accessible in any way other than for rewards claiming, and the ledger is incremented in the consensus registry to sort of delineate what amounts should be delivered to which addresses. But one interesting nuance is that for maximum optionality in the worst case scenario, the issuance contract perhaps is not topped up in a timely manner by the TAO. And so the rewards ledger continues to be updated, but claims are allowed to fail, essentially, so that the issuance contract can be topped up asynchronously based on, if there was some governance holdup or some black swan event happening, then the the issuance contract and the consensus registry are designed to handle those and provide the information to retroactively issue those funds. The issuance contract basically offloads accounting for issuance to its EVM native ledger. So the balance of the issuance contract is equivalent to the funds that are allocated for issuance on an epic-wide basis. And rewards are calculated based on node performance. So a validator, a node operator who proposes a large amount of consensus headers. The number of consensus headers is essentially linearly tied to the amount of rewards once weighted for stake. So stake amounts, one thing to know there is that they are configurable. So the stake amount, the principal, if you will, sort of determines what fraction of rewards multiplied by the number of consensus headers proposed. So it's a weighted calculation is what I'm getting at. Stake versions are tracked. If they are changed, it's not intended to be used often, of course, but maximum optionality as a first principle leads us to have stake versions be configurable, the staking amounts, the epic duration, such things. Delegation is supported. I discussed that already. Rewards, sourcing, and balance tracking are here. Just some simple little one-offs. There's a pull-only claim. So then there's a minimal potential for reverts, minimal potential for reentrancy. Consensus block rewards are fully funded by the TAO. It may be explored in the future that inflation of the native ledger on the protocol side is implemented, but at the moment the TAO is sourcing the issuance rewards, and validated balances use a U256 ledger. This includes both their stake and their accrued rewards. Yeah, so that is the design file for the consensus registry. I have a number of invariants here. I'm not going to go through all of them, but they are important. Any violations of these invariants, and I believe none of these are outdated. They should all be up to date. So any violation of these would comprise a valid finding. These should be very helpful in examining the code, understanding the intent of the implementation. So I just wanted to point that out. And this is the consensus registry interface. This will be a major place here to observe data structures, flows, functions, validator lifecycle, documented system calls. These are the three that we've mentioned, as well as functions related to the validator lifecycle and read functions, which are helpful for verification off-chain or are used also by the protocol itself on the Rust side. The consensus registry, like I said, also has a parent abstract contract implementation called the stake manager. So the iStake manager interface will be another place to observe important information structures, configuration, data structures, delegation struct, like I said, with the sort of very involved handshake process, as well as functions related to the staking and the consensus NFT ledger, so they can get the stake configurations, the stake versions, the balance for a validator, the current issuance contract, the allocation of issuance to be called by governance. So the gist of it is that these interface files should be very helpful for looking through the code and cross-referencing the actual implementations themselves. Cool. So moving on to the Interchain Tel contract. This is the other major system contract that is critical to the Telcoin network blockchain. And the overview of it, I'll make a prettier view of the Interchain Tel contract, is that it is an Axelar Interchain Token Service compatible ERC20. It wraps the wrap tel, which is equivalent to WETH. We're using the Solidity WETH implementation, and that is the wrap tel contract, which can be used in DeFi, NFTs, other sort of application, or I should say smart contract layer protocols. So the iTel, the Interchain Tel, wraps the wrapped tel, has its own ledger for it, and offers certain extra features which are related to the Axelar Interchain Token Service, as well as just general security measures. So the Interchain Tel module, it facilitates conversion between the original ERC20 Tel token, like I said, was an ICO in 2017 on mainnet Ethereum, and between the Telcoin network's native Tel gas currency. So that conversion is really important because the ERC20 Tel on Ethereum is the canonical ledger for that token, the canonical supply, the canonical token, period. And that token is intended to be imported to Telcoin network, where it can be used as gas currency. It can be wrapped into WrapTel, used on the application layer for various DeFi NFT protocols. And it is designed to be interchain natively, and so it should be portable to all chains that support the Axelar Interchain Token Service. And this is if you're not familiar, that is a sort of on the cutting edge of interoperability standards, not just to EVM chains, although EVM chains have the greatest market penetration and developer mindshare. It also is opinionated enough to be usable for other chains like Cosmos IBC and Bitcoin and Solana and that sort of thing. Excuse me. So one thing to note is that the Axelar Interchain Token Service, they are integrated as Genesis system precompiles. They are Solidity contracts. The EVM bytecode is written to their addresses. The certain contracts within the protocol, including the Interchain Tel contract, and its token manager are written as in Genesis with a certain storage configuration to back. This also applies to the consensus registry, mind you. It is a custom implementation of the Axelar Interchain Token Service. So the Axelar ITS offers essentially 3 different kinds of ITS compatible token standards. We've opted for the custom linked one. So we will be using a custom linked Axelar token ID, which is a UID that identifies a token across the Interchain ecosystem. And so the token manager that goes into Genesis as a system precompile is the one that handles the minting and burning, which have a direct relationship to minting and burning or locking and unlocking on remote chains such as Ethereum or Polygon or what have you, which sort of maintains the integrity of the Tel supply and its ledger. There's an additional contract which is important to point out to add security in a time lock fashion. We've used Circle Research's recoverable wrapper utility, and this is, like I said, sort of the wrapper around the wrapped Tel ERC20 representation of Tel. And this double wrapping allows us to enforce a time lock on outbound Tel, so that Tel destined for remote chains in the bridging architecture is enforced to wait a certain amount of time before it can be sent off chain, and that is largely a security feature. Yeah. So essentially that covers most of what Interchain Tel is doing. The Interchain Tel contract at Genesis is allocated the total supply of Tel, the native gas token. It is inaccessible to anybody, even the governance contract, unless a valid ITS message, which is verified on Axelar network and cross-referenced against the finality of the source chain, and signed by a network of verifiers and relayed by a number of relayers that is the only way to access the total supply of TEL at Genesis. There is one caveat to this, which is that 10 TEL are allocated to the governance safe at Genesis, which is included as a system precompile with its storage configuration, so that it can pay gas for the first interchain steps. There's a number of linking steps and sort of enabling steps that need to be taken, including relay of TS messages from Ethereum in order to deliver TEL or import it to Telcoin network from Ethereum. These are documented throughout the repo, this process, but essentially the one way to abstract it is that the TAO governance safe would serve as the first relayer for Telcoin network, essentially just to import TEL, more TEL, but in a way where gas can be paid from Ethereum. So then going into the Interchain TEL design file, this should be helpful in understanding the Interchain TEL architecture. There's a number of moving parts. A lot of these, like I said, are system precompiles instantiated at Genesis and are required by the Interchain token service. So this, I won't go into full detail for the sake of time, but some of the takeaways to keep in mind are that Telcoin network, like I said, uses TEL as its native gas currency. This will be imported from Ethereum's ERC20 TEL, and it does so with the ITS integration. So it's a custom linked token. It has a mint burn token manager, and the recoverable wrapper contract is an important. And in scope, mind you, it is a fork of the Circle Research's published recoverable wrapper, and so it is in scope because we have deleted some of its functionality and we wanted it to have more audits under its belt. It was published in 2023, and we just wanted people to have a fresh look at it as part of this competition. I'm going to talk about double wrapping. So TEL has to be wrapped to WrapTEL and then to ITEL. The supply allocation I already went over. Flexibility as the custom link token IDs is sort of one reason why we picked that, was the flexibility, the maximum optionality as a first principle. These are the steps that will need to be taken by safe. And we also have an ITS design file here, which goes into the Axelar Interchain token service, which may be helpful for understanding the context overarching our implementation decisions. I won't go into this, but a custom linked interchain token would be the type that we chose, although we discussed the other things here as well. Lastly, to finish up, as I said before, the interface for each contract will generally be the best place to look through each of the contracts, with the exception of code that was not written by me, such as the recoverable wrapper. Again, this is a Circle Internet Financial publication, and so their documentation is done differently than I would have done it. But this contract is in scope and worth a look, because we would like to ensure that it is battle ready for our purposes. But generally, the interfaces will be the place to look for documentation, information about each function, the double wrapping, the support for permits, ERC 2612, some of the Axelar functions that are required for yes, as well as the functions that actually perform the delivery themselves, and some notes on decimal handling, which are handled by the Axelar Network DS Hub. So that is TN contracts in a nutshell. I'm just going to look through, make sure I didn't miss any files that would be in scope. The tests are relatively straightforward. We've got fuzz tests, we've got fork tests. You would need to provide RPC URLs to run each of those. But in essence, that is TN contracts. So thanks for watching and happy hacking.